Let's explore how to implement iterators in C++ using a tier list data structure as our example. A tier list is a collection of multiple lists organized in tiers, and we need an iterator to traverse all elements across all tiers seamlessly. Let's start by reviewing the basic iterator pattern from a simple linked list. A basic list iterator stores a single pointer to the current node. The iterator maintains a pointer that moves through the linked list nodes, advancing from one node to the next. The increment operator simply advances the pointer to the next node in the list. Now let's understand the challenge of iterating through a tier list with multiple separate lists. A tier list contains an array of separate lists called tiers. Each tier is its own linked list with different numbers of elements. The challenge is making the iterator move smoothly from the end of one tier to the beginning of the next tier automatically. A tier list iterator needs to track more information than a simple list iterator. The iterator needs three pieces of state: a pointer to the parent tier list, the current tier index, and an iterator for the current list. Each tier list iterator contains these three fields: a pointer to know which tier list we're iterating, an index for which tier we're in, and a list iterator for our position within that tier. The increment operator is where the magic happens, handling tier transitions. When we increment, we first try to advance within the current tier, but if we reach the end, we must jump to the next tier. When the iterator reaches the end of a tier, it automatically jumps to the beginning of the next non-empty tier, creating a seamless iteration experience. After advancing the list iterator, we check if we've reached the end of the current tier to determine if we need to jump. A critical helper function is needed to skip over empty tiers. This helper function searches through the tier array starting from a given index to find the next tier that actually contains elements. The function scans through the tier array, skipping null or empty tiers until it finds one with actual elements, or returns a sentinel value if none exist. If no non-empty tier exists, the function returns tier count as a sentinel value, which we use to represent the end iterator. The begin and end methods create the boundary iterators for the tier list. The begin method uses our helper function to find the first non-empty tier and creates an iterator at the start of that tier's list. The end method creates a special iterator with current tier set to tier count, serving as a one past the end sentinel. The begin iterator points to the first element across all tiers, while the end iterator serves as a sentinel, marking the boundary past the last element. Comparing tier list iterators requires checking both the tier and position within the tier. Two iterators are equal only if both their current tier index and their list iterator position match exactly. The not equals operator is simply implemented as the negation of the equals operator, following standard C++ practice. Let's see how all these pieces work together in a complete iteration example. Starting at begin, the iterator advances through tier 0, then automatically jumps to tier 1 when reaching the end, continuing until all elements are visited. From the user's perspective, iteration looks just like a single continuous sequence, with the tier jumping logic completely hidden. Let's review the essential components needed for a tier list iterator. Store a pointer to the parent tier list, the current tier index, and a list iterator for position within the tier. Implement a helper that finds the next non-empty tier, returning tier count if none exist. The increment operator advances within the tier, then checks if a tier jump is needed. Begin finds the first non-empty tier to start iteration, while end uses tier count as a special sentinel value. Iterator comparison must verify both the tier index and the position within that tier's list match.